Hello, everyone. I think we're currently live, so welcome to Zaka's Live. And we're so happy that you're tuning in right now. We have two speakers, researchers technically, that are joining us today. And I'm really excited to share that I met them this year at Al Medina, Saudi Arabia. And I was really amazed how they took their research experience and really built to start up and launch them. So today they will be talking more about how they were able to combine their experience and to bring their research experience um, into a startup. So I'll leave it to Samaher and Zied to introduce themselves. And if you didn't introduce yourself yet in the chat, please do so. We have already participants who are sharing where they are tuning from. So we have Vikram from Netherlands. We have Khalil from London. Muhammad, I assume you're from Lebanon, from UAE. We also have, so please share in the chat where you're tuning from. And if you also want to be the first to know about our upcoming, if you want talks, because we're always bringing researchers or also speakers in AI to share their experience, make sure you go to our website, zaka.ai, and you subscribe to our newsletter. So thank you everyone for tuning in, and Samaha and Zied, I leave it to you to introduce yourself and take the floor.
Okay, yeah. So thanks for having us. Really appreciate it. My name is Zied. I'm the one of the co-founders of Myelin H and Myelin S. And aside from that, I'm an assistant professor of neuroengineering and robotics in Manchester. And I was nominated as one of the top 10 most innovators back in 2019 by NASA, and also was endorsed by the Royal Academy of Engineering as one of the kind of global talent in the UK. And I'm here today to present, co-present actually with Samaher what we've been doing over the last few years in terms of R&D, as well as how we translated this R&D into commercial companies. And yeah, this is me, and I'm done speaking. I just hand over to Samaher to talk about, to introduce herself, and then we get the ball rolling. And thanks for joining us today.
Thank you, Ziad. So hello, everyone. I'm Samaher. I'm engineer by training. I hold mathematics and applied modeling engineering, and the second master in space robotics. I co-founded the two companies, Myelin H and Myelin Space. So, and we are now here to introduce more our companies, what we did in research, and now in the market. Yeah, thank you.
Okay, so let's just get the ball rolling. So today's presentation is basically talking about how we are combining brain-computer interfaces, and will be introducing this concept with machine learning. And it's what we call neuromorphic computing, which is a biologically inspired machine learning. It's a bit ahead of the curve compared to machine learning, standard machine learning techniques, to solve healthcare and space exploration challenges. And you see, be able to connect the dots and see the connection between healthcare and space exploration. So my name is Zied. As I said, did my PhD in the area. And I think the first half of the presentation will be just talking about my research and what I did during the PhD. And I'm joined by my co-founder, Samaher Gabay, who will introduce a bit more how we are commercializing this research and translating this into commercial companies. So the first thing we'll start with is basically demystifying the concept of brain-computer interfaces. So BCI has gained momentum over the last few years and has been widely used in different and various applications. One of them is this video here, where you basically say helped make the start of the 2014. So it's a tetraplegic patient was able to. So a tetraplegic patient was able to kick the ball during the Soccer World Cup 2014 using an exoskeleton, so a completely paralyzed person. And this marvelous work was done by my PhD advisor, Professor Gordon Cheng, where basically they built this exoskeleton. It's a human body, like a whole body exoskeleton, and then the subject was able to control the exoskeleton using just thoughts. And this is a very, very good way, or very good example of what BCI can do. This was a really fabulous moment during the Soccer World Cup. So some of you may have watched this. The second one is the work done by Chris Noshnoy and his group at Stanford, where again, a completely paralyzed person, a lady, was able to control and write sentences and communicate with her loved ones using just thoughts. So basically, thoughts from the brain, they were translated into text using the concept, very well-known concept in BCI, whose name is P300. It's a positive deflection in the brain signal, what we call the EEG, appearing 300 milliseconds post thinking or giving attention to specific letters. So you see keyboard, a couple of letters being flashed, and then the lady was able to control that. Another example, which is a funny one, is the using BCI to compose music for non-experts. I'll let you just hear the music that was composed by completely non-professionals using just thought. So as you can see here, it's a couple of letters and notes. They've been flashed on the screen. The subject had to give a specific attention to each of those letters, and then they were decoded using machine learning. So it was a simple support vector machine classifier that was able to decode thought, and then quickly, using a few training sessions, the subject were able to learn how to compose music, and just jumped directly to the composed music. So here is what the non-experts were able to do after 1.5 hours of training using thought. This is completely kind of brain decoding rather than playing music directly. And the last work I want to touch upon, or just shed a light on, is the one I did with my students. So one of my students, when I was at the Technical University of Munich, we were able to control a robotic arm using just thought. So basically, someone had to watch each of the, so I had to just focus on one of the 4 flickering checkboards. They do blink at different frequencies. Those frequencies, they were propagated from the eyes to the optic nerve to the back of the head, and they were decoded using, again, very simple machine learning. I think it was a linear discriminant analysis. And then from that, they were translated into commands to control a robotic arm, an industrial one. And you would say that whenever the subject, for example, focused on the right side of things, the robotic arm moved right, again, using just thoughts, or vice versa. So if you focus on the left side, the robotic arm would move left. So as you can see here, though they do flash randomly at different frequencies. For example, the subject, I think there was asked to focus on the bottom side of things on the screen, and the robotic arm was controlled thereafter. Yeah, it was focusing on the left side. The robotic arm moved left. I can just go quickly show you this another one, another comment. So when the subject focused on I think it might be the right side or wherever. And then the robotic arm was controlled accordingly. Yeah, it was right side. Okay. So it was just in a nutshell what you can do with BCI. I think you can do way better things, but it was kind of the tip of the iceberg of what you can do with BCI. Now, specifically in my research project, what I was investigating is the usage of combining multiple biosignals, what we call EEG from the brain, EOG from the eyes, and EMG from the muscles. And those signals, they were decoded in real time and then translated into commands to control a prosthetic hand. So we had people who lost their arms, amputees, with a prosthetic hand, and they were able to control using brain signals as well as muscle activity, as we do with our normal limbs. They were controlling the prosthetic hand, and simultaneously we had different sensors on the fingertips of this prosthetic hand, and those signals, they were again translated using machine learning into some electrical stimulation. So basically, we were rewiring the robotic hand with the residual part of the brain of the body, which is the residual muscles and nerves. and then we gave sensation to that patient. So they were able to distinguish between very sharp and pointy objects versus round curvature, or very soft materials versus hard ones, or for example, very hot and very cold objects. And we were using EEG, or the brain signal, to understand how the brain perceives those external stimuli. So it was more a bidirectionally controlled prosthetic hand towards the revolutionizing prosthetics and kind of body extension and what you call cyborgs. So the first study, to be very specific, so the first study was intended to just decode thoughts. So how can we use deep learning, or leverage deep learning, to translate random thoughts? For example, just imagining moving your right or left hand into a decodable movement so that you can control a robotic arm or a prosthetic hand, wherever. So we recruited 20 subjects. They were healthy control as well as patients. They were instructed to just imagine passively, without actually moving the arm, to passively think about moving their arms left or right, or both hands at the same time. And then we acquired the EEG signal, which is brain signals, as you see, using this EEG cap. That signal was translated, so was processed using different processing techniques like wavelet and Fourier transform and different things. And then we developed a feature matrix just to decode the signal. And then we used different deep learning approaches to decode the signal. So we were looking for a specific event, which is what you call evoked potential, as you see here. When someone imagines moving their left arm, then you can see a power decrease in alpha, which is a very specific frequency in the brain. And that was translated into movements. So as you can see here, because this is a 1D signal for those who are technical, we had to convert this into an image, so using a spectrogram. So one axis is time and the other axis is frequency. And then from those spectrograms, we used a fairly well-known convolutional neural network architecture to train images taken from the brain. And then from that, we were able to control a robotic arm. So basically, a CNN was trained to distinguish between different spectrograms coming from different sources, either left arm movement, imagination, or right arm, wherever. So here is the simple CNN architecture. So you see the Roman EEG was recorded from the brain, was converted into spectrograms. Then we went through a normal 2D convolutional layer, and then etc. For those who are interested, we can go through the detail of how the implementation was done. And then, as you can see here from this circular plot, you see we did implement a couple of machine learning techniques, like the normal ones, like nearest neighbors, logistic regression, naive Bayes, all the normal standard machine learning techniques. And then we compared them to our deep learning approaches, CNNs, LSTMs, recurrent convolutional nets. And you can clearly see that the deep learning approach, specifically our proposed CNN approach method, outperformed the other machine learning techniques very, 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 very clearly. And here's a quick demonstration of the whole thing. So a lady, a patient, was instructed to just imagine moving her left or right arm without any active movement, just passively think about the movement. And this movement was decoded using the CNN, and then was translated into control commands to control a robotic arm. Again, what we see in science fiction is completely wireless communication between the brain and the robotic system. So she was thinking about, she was thinking about right movement, the robotic arm went right, whereas when she thought about the right movement again, the robotic arm went right, and then, so this is the signal we were taking from the brain, and then it was translated into spectrograms. And then it keeps going. It was very good model, so we reached 90% accuracy. We reached 92% accuracy. And this paper, I think I'm very happy that this was among the very first work to basically decode brain signals using spectrograms and leveraging deep learning to decode EEG, and then use that in the context of human-robot interaction. That paper has received more than 105 citations in the last 2 years, and it was selected as the editor choice article in 2020. And by the way, this is the foundation of what you see there down the line thereafter in the startup context. As we are just talking about the science, but be kind of moving to the commercial aspect. Another thing I want to quickly touch upon is the neuromorphic computing. So this is the concept we've been using in the startup as well. Unlike traditional deep learning approaches, we did realize during that study that it's very computationally heavy, and it consumes a lot of power, and also very slow, as you may have seen from the demonstration. It takes so much time to process signals. So we had to come up with another idea, how to circumvent those issues. And the main idea was to leverage what we call neuromorphic computing. It's about completely biologically inspired. Instead of fixed weights and doing back propagation to basically learn, we have synapses and neurons. They are connected. They fire when they fire, and they encode temporal information inside the brain. It's more the way how our brain works, because our brain doesn't do any back propagation to understand and learn. So we implemented two different algorithms. Both algorithms were taken from, or inspiration was taken from biologists. The first one is the olfactory system of insects. We used that from bees to basically decode brain signals. And the second one was more a liquid state machine. And both they were implemented in a specific hardware whose name is Spinnaker. It was developed by the University of Manchester. We've been able to show that without any handcrafted features, without any spectrograms, whatever, with raw data as it was, we were able to get the same accuracy or even better. But we gained also in terms of power by 40%, to reduce power consumption by 40%, and it reduced latency 4 times. So we were able to do the same computation, but 4 times faster. And I mean, you can see the papers, they are all just done. If you just Google my Google Scholar, you see the papers and you'll be able to read what we've done. Now let's move to the second slide, kind of a bit more advanced than what we did in the first study, because we did realize that it was very limited. It was just 4 movements, and obviously, as you do with your hands, you need to have a dexterous manipulation. You do a lot of reach and grasp movements, so we needed to combine multiple biosignals. And this is the idea where we had to develop EOG and EMG decoder, so basically to do reach, grasp movement, so complex movement. So we recruited a couple of patients, or I think it was a normal, healthy control subjects. We recorded the EOG, which is from the eyes, as well as combined with the EMG. And the idea was to decode the reach to grasp movement using this context of human-robot interaction. As you can see here, so we used a simple machine learning algorithm, but it was a sequential way. So we had a probabilistic model. And you see, after performing the principal component analysis, it was highly, very, very easily classifiable in terms of the classes, up and right. So the subject was asked to basically move the eyes up or down, left and right. There was the reach movement that was decoded, and then afterwards it was the EMG. So they were instructed to contract their muscles when the object is very close, or when the robotic arm is very close to the target, and then it was decoded fairly good. You see in this demonstration, hopefully it will please you. So this is me in here. And then the subject is a completely teleoperation mode. So as you can see, someone is sitting on Earth and someone in the robotic arm is somewhere else in a very dangerous, extreme, harsh, uneven terrain. The subject had to imagine just moving their eyes left to right based on where the object is being pointed by the lady. So the lady, for example, pointed the object towards the left side of things. The robotic arm went there, again, with just, human intention of moving the arm. When the object was very close, the subject performed an EMG contraction, a muscle contraction. The object was grabbed by the arm, and then now the lady is asking for the object to be back again, but it's up left. Again, the subject just moved the eyes accordingly. The robotic arm, again, with no cameras, no assistance, figured that out immediately, and then there was a release action, again, based on the user's control action. So it's a very good way to demonstrate this real-time human-robot interaction. Now the lady is asking for the arm to pick the object on the right up, and then you see the robotic arm goes there again with no cameras. It's only the human controller who's sitting somewhere else. It's controlling that, and then it grabs the object based on human instruction, and then it goes, etc. Okay, let's just go again. Now let's focus on the other side of the equation. So one of the things I did when I was doing the PhD was with the National University of Singapore, as well as Johns Hopkins in the United States in Baltimore. And what we did here is we developed a sensory-enabled prosthesis. So basically, people who lost their arms and legs, they can feel with their prosthetic hands, for example, level of sharpness. They did develop the sensors. I was not involved in the study. I was involved in another study where basically they were able to distinguish between very sharp and pointy objects using their robotic arm or robotic hand, and they were also able to have a withdrawal reaction. So if you touch something which is very hot and cold, or cold, it just immediately move away from the target. And this is what we want to have inside the arm as well, or the hand as well. So this is a work that was published in Science Robotics.
Upper limb prosthesis users generally want to see improvements in control as well as comfort, but there's also a component of sensory feedback that users are interested in. So these pain sensors that we've made go over the fingertips of the prosthesis, and they can detect both touch and pain. We're calling the device we made an e-dermis, so an electronic dermis. And what's particularly interesting is that we're able to detect, say, object curvature. And so we can differentiate between something that's nice and rounded versus something that's very sharp and pointy. And that's what lets us be able to differentiate between something that's painful or not. And so with the sensory feedback, we can provide natural sensations to the phantom hand of an amputee. And this is really important because it's taking one more step closer to having a lifelike upper limb prosthesis.
So Lucas Bourne is one of my collaborators. We did publish a couple of papers. I was involved in this study, and as you can see, we did this in, using different methods. One of them was Vibro tactile, as you can see here from this video, where was basically I was blindfolded, as you can. So this is me here. I was blindfolded, but I was receiving sensory feedback using Vibro tactile stimulation. I was able to distinguish between very soft object, which was a sponge, versus a hard object, which was a charger, and so forth, so on and so forth. So you see here, you hear me saying soft and hard and medium. So I was saying hard, and we did this with a couple of people. So this is another experiment. So for example, normally should say soft. Exactly. All right. So there was kind of the work I was doing in terms of prosthetics. I mean, we built a pain reaction system inside the prosthesis. We're trying to go one step closer to having a real-time kind of natural hand as we have with our biological hands as well. And we did publish this in Nature. So it was published in Nature Scientific Reports, where we built a complete pain reaction system. I won't go into details because it involves a lot of sensory feedback and neuroscience to understand how the brain controls limbs and nerves and so on. But the experiment, as you may have seen, we had different objects. The subject was touching different objects. We had a very accurate sensors on the fingertips. We were able to take that signal, rewire the prosthetic hand with the residual nerves, and then patients were able to feel with their prosthesis what they would feel with their normal hands. And then we used EEG as a way to understand how does the brain perceive that. And the idea was to try to alleviate phantom limb pain, which is a very common issue in prosthetic devices. And then we did a lot of analysis, like source localization, going deep into the brain and trying to understand different brain parts, how they react. As you can see here, when you touch something which is very sharp and pointy, you see some kind of reaction in the brain inside the ACC, anterior cingulate cortex, which is a region for attention. So we did a lot of neuroscience analysis, but I won't go into details. I think but if someone is interested, the papers are out, and I'll be happy to answer any questions in there. But obviously, it involves a lot of machine learning as you take the signal, you process it, you decode it, very noisy signal. You do apply a lot of machine learning, a lot of signal processing, and we've been able to get up to 95% accuracy when distinguishing between the different stimulation patterns from the prosthetic hand and in the brain. And based on that, you can see the confusion matrix, the latency, how we did the signal processing. But again, if you're interested, I'll be happy to go through the details. This paper was nominated for the BCI award, which is the International brain-computer interface award in the world. It's kind of the Nobel Prize in our area, and was selected as top 100 in neuroscience papers published in Nature in 2020. And we have contributed to the scientific knowledge. We've got a very specific understanding of neuroscience and how the brain controls limbs. And along the same lines, I think the other study was almost the same, except that we wanted to understand thermal perception in the brain. So instead of having different objects with different levels of sharpness, we focused more on the thermal sensation, so very hot, very cold, and then we did the same. You see here, this is very quickly the experiment where different people, I did this experiment in Singapore at the NUS, where basically, let's see, the video is not displaying itself, or maybe it just yeah, so as you can see here, we've got different objects. Each of those had different temperature. The subject was blindfolded, as you can see here, and they were instructed to touch those objects randomly. So it's a wide spectrum from very cold to very hot and everything in between. So 5 different temperature stimuli. And then from that, we controlled, so it was used for the context of human-robot interactions. We did understand how the brain perceives each individual temperature stimulus. And then we translated this into ways controlling a humanoid robot, as you can see here. And this is, again, in the context of human-robot interaction. You'll be surprised that this is the context or the concept we are using for our space venture. And I'll show you the demonstration with the robotic system as well. But there were a lot of neuroscience involved, processing data, understanding alpha and brain reaction. Again, a lot of neuroscience, but I won't go into details unless you want me to do that. And obviously, we've been relying on machine learning. So linear models here, and some biologically inspired, like spiking neural nets, and to decode the different. So to decode the brain response to each individual temperatures stimulus, and sometimes it's coupled. So we were able to use the brain signal to distinguish between very hot and very cold objects, or very cold and cold, etc. And here is a cool demonstration of the whole thing working in the context of human-robot interaction. So you see here, it's a industrial robotic system with sensors everywhere. So basically what we did implement here is the 3 different reactions to different objects. If the object is very hot and very cold, you see immediate reaction. It's the same way how we humans would behave when we touch something which is very cold and hot. Take immediately our hands. Slow reaction when the objects are cold and hot, which means are manageable. And if the objects are innocuous, which means warm, then you see a very, very slow reaction. And this is, I think, again, taking one step closer towards having a full bidirectional human-robot interaction. So the first thing is, for example, if the robotic arm approached, so you see here is the robotic arm approached the object, it was very hot. The machine learning predicted this is very hot correctly, and then an immediate reaction away from the stimulus. This robotic arm was controlled using thought from another external teleoperator outside the room. So the object is warm. The predicted using machine learning is warm as well, and then it's a very slow reaction, as you can see. And this is exactly how we humans would react to this, and it goes this way. It's very cold, the immediate reaction, and so on and so forth. Very quickly, just want to touch on another thing very, very quickly. So this work was translated also into initiatives inside the university. One of them is the Cybot loan. It's a very well-known competition taking place at ETH Zurich every 4 years, where people with disabilities, like amputees, people who lost their arms, tetraplegic patients, they use their assistive devices to play against each other. It's more kind of marathons, competitions. We set up a team from the Technical University of Munich. They competed, and I was kind of one of the guys who were doing this and managing and supervising students. This received a lot of media coverage, and it was featured on the Technical University of Munich's website. And you can see here, it's just very quickly, people play games with thoughts, like people with disabilities. They play, for example, Super Mario's. They're completely disabled, or they play different things. And then it was also translated into what we call Think, Make, Start, which is a 50-day workshop where people they come up with ideas and startups using this concept of brain-computer interfaces. I also published an open source software which has been used by more than 25 universities across the world, whose name is Gumby. So feel free to use that software. It's the open version, the academic version of what we're doing from the commercial perspective. And we decided to keep that open. So many universities are using that. If you want to do brain-computer interfaces, deep learning signal processing with complex biosignals like ECG, EMG, EEG. And obviously, this one hand can never clap alone. So there was a lot of work and people who supported me behind the scenes, my supervisor, my students, and a couple of other partners like the University of Manchester, Johns Hopkins, and so on and so forth. Let me jump to so those are the papers published. We 6 journals, 2 Nature papers, conference papers, awards, and so on and so forth. Very quickly before I hand over to Samaher, just to walk you through the startup experience. So we started the first company, which is based on the same concept, whose name is Mind and Age. And the idea was to use this BCI knowledge, the way how we decode the EEG to help better manage brain diseases. And the whole story stems from a personal one. So I started this company after my mother was late stage diagnosed with multiple sclerosis, a very tough brain disease. And it took her 3 years to realize that she suffers from MS, but more importantly, she was taking the wrong treatment. It was inadequate because she was secondary MS, but she was taking treatment for primary MS, and this led her to being fully disabled and unable to work anymore. On that basis, Samaher and I came up with the idea of developing this BCI kind of as a SaaS, software as a service company, where we're trying to, our mission is the right treatment for the right patient at the right time and under the right circumstances. The company was incorporated in Luxembourg, and we've got now offices in Belgium and Manchester. We've received financial support from the government as one of the most innovative companies back in 2021, and we've been able to generate revenue. So we work with a couple of hospitals, including the University Hospital of Leipzig, and we've got some financial revenue traction. And also we work with Langone Medical Center, which is one of the largest, Langone Medical Center, by the way, they pronounce it in New York, one of the largest MS centers in the world, and Helios Park in Germany. We've received a lot of media coverage, and we are backed now by a private investor, which is IMEC, iStart Venture Fund. So the company is me, an assistant professor in the area. Samaher holds 2 master's degrees in the area as well, and 3 different medical doctors supporting us behind the scenes. We also work with Stanford Medicine, Professor Sharma K from the pain medicine group. And as I said, I think I'll walk you through the story. It was a personal one. My mother wasn't able to do kind of remote monitoring of her situation and disease progression without undergoing lengthy and very tedious MRI kind of process. And overall, there are more than 1 billion individuals suffering from neurological diseases, like 50 million suffering from Alzheimer's disease, for example. So the concept, as you can link it and connect the dots with what I have presented in research, it's a dry, very simple EEG system. Usually it takes roughly in hospitals 1.5 hours to just get the system, record the data. But our system takes less than a minute. We capture 4 different signals. When we capture the signal, the patients or users usually have to play different cognitive games, and each game is supposed to assess specific brain activity, whether it's attention, whether it's motor control, whether it's visual spatial attention, different things. So we've developed up to 10 games, and once you play the games, then we record the data. We apply, again, I don't like to call it machine learning with neuromorphic processing because it's a bit ahead of the curve. But anyway, we decode the signal and then we translate it into a very powerful PDF medical report that the doctor can see instantaneously, anywhere, anytime, regardless of the patient location. And the idea, the mission we're going after is basically digitize the healthcare and helping those patients better manage their diseases, help doctors adjust medication doses remotely towards, and also contributing to advancing clinical trials and drug discovery for those diseases. I'll hand over to Samaher to walk you through the space combination, or how we do this from a space perspective.
Yeah, thank you, Zied. So let's talk about our space medicine product. Yes, yeah, thank you. So here our product proposes a hybrid and closed-loop BCI system that relies on the real-time processing and decoding of four biosignals, so the EEG, the EMG, ECG, and the EOG, to assess astronauts' overall health. And in parallel, we use the same system to train the astronauts by playing different games to improve their abilities. So go to next slide, please.
Yeah. Okay.
Yeah. So generally speaking, we developed a novel machine learning, as Ziad explained before. So the software is capable of detecting and analyzing a complex biosignal patterns in less than 2 minutes using wearable signals. Then the user would play our neuro games. We analyze and interpret this data in real time, and we turn that to a medical report and send it to a doctor. And Ziad, please. Yeah, using our technology, we have three different products. The first one is the medical research product to accelerate clinical trials and drug discovery. And the second one is for monitoring multiple sclerosis patients, is mainly to stop the disease progression and tailor the medication. And the third product is the Space Mirror, with the space medicine product to monitor astronauts to to prevent diseases and the space effects. And now let's move together to the second company, which uses the same technology with slightly different applications, which is space robotics. So our company was selected by NASA ITech as one of top 10 innovations in 2019, and for autonomous applications in for space systems. And now we are supported by the UK Space Agency. So let's go to the next slide, please. Yes. So in fact, the whole story started following the research, for sure. We realized how important to have more autonomy in robotic systems, in terrestrial applications, and in space applications too. Yeah, Ziad, go. So on that basis, we are developing a power-efficient software operating system that acts as autonomous brain for terrestrial robots and spacecraft. This operating system makes robots more autonomous and can be teleoperated by humans in real time. So the Brainlike Platform has embedded, yeah, has embedded into different modules. The first one has algorithms for onboard sensory information processing and decision making, whereas the second one runs these algorithms more efficiently compared to the classic AI by using the neuromorphic computing. Yeah, go yet. Here is our executive team, so composed of business experts and subject matter experts in space, robotics, and machine learning. As Ziad, the CU, is assistant professor in Manchester, and also he has a PhD in the field. I have two masters in mathematics and space tech. Our third co-founder, she is the CEO of Singapore and Space and Technology. We have also advisors from NASA, JPL, European Commission, and also different other universities with expertise in robotics mainly and in business too. Those yet. So there are four applications in terrestrial applications. We work in mining, robots, and oil and gas. And the space applications are in satellite observation, in orbit servicing, as well as the space exploration. Okay, so far we have published already 5 papers, and all started from the open source software. And we already have different 4 customers, which we are now starting the pilot projects. And also we have different partners in universities and BP company and different other companies, as well as awarded from different space agencies and organizations. And thank you so much for hearing us. We are always looking for good brains. So if you are excited about what we are doing, please reach out to us. Thank you.
Yeah. So I think, yeah, let's park it here for now and open the floor for
Yeah.
questions. Very much excited. If someone is excited and want to come along for the ride and come with us, for this journey, please do not hesitate to contact us and reach out to us using the email address. We are, again, as I said, as Samaher said, we are always looking for good brains who would be kind of willing to put sweat and tears and support us down the line. Thank you so much. This is me, and I'm done speaking. Thanks for having us, and I'm very much looking forward to your questions.
Thank you so much for the presentation. We have actually a question in the chat. Not sure if you can see it. So let me know. Otherwise, I can read it for you.
Actually, I see so many questions, isn't it?
In the last one, Kamal is
Oh,
asking.
no, there's only one or two.
Yeah, I'll show it here in the chat.
Okay, so when dealing with PCI, specifically using robotic arms, how did you go about damping the robot's response based on machine learning output?
There's a follow-up also, Zied.
Okay, so BCI, specifically using robotic arms or prosthetics, how did you go about figuring the robotic arms response to the output of the machine learning algorithm? So as not to execute too sudden slow movements. Yeah, so I think given the way how this is being done is basically we look for what we call evoked potential, which are external stimuli. They generate specific patterns in the brain. Once those patterns have been recorded by EEG or the signal, we process the signal. So we have a time window for those who know machine learning. So we have a specific time window, which is, let's say, 1 second, where we gather data. We process that data, whether it's a spectrogram, as we did with the deep learning, or whether just a normal extracting some basic statistical features using normal machine learning classifiers. And then from that 1 second, we generate a ROS command. It's basically robot operating system command, which is locked to that one second, which means, and then from that 1 second, we generate an automatic response for the arm to move. And then based on that, once the movement has been achieved, which is again using the internal controller inside the arm, then we send back the feedback to the classifier to trigger again, to take another additional 1 second, reprocess, redecode that 1 second, and then translate it into a second command. So I hope this answers the question. But this is how kind of the system is being implemented. And if in terms of if the question is touching upon the accuracy or kind of the latency, so being able to use neuromorphic computing to accelerate that latency by not handcraft any features, but rather rely on raw data directly, and they've been able to gain specific kind of reduce latency by 4 times. Yeah, it's a direct translation, as you're saying. I'm just using your own words. It's a direct translation of brain activity into commands to control external devices, specifically, robots' actions and arms.
Okay, great. So I think if no one has any question, you can reach out to Zied and Samaher on the email. We'll make sure to drop it by in the email. So make sure if you want to hear maybe other speakers, we always, so we have another question. So we make sure you follow us on social media platforms and you subscribe to our newsletter. So we'll share with you the link and the email to Samaher and Zied startup. So yeah, we have maybe another question now.
So the question is, what types of behavior do you train robots, space ones? So basically what we do in the space context is we try to generate what we call curiosity. So we as human beings, we are very curious, we want to explore. And one of the issues with deep learning is you have to train your system based on set of instructions what to do at each individual circumstance, but because the environment is very harsh and uneven terrain, it's non-deterministic, which means you can't rely on pre-trained models to train your system to do X, Y, and Z, and for example, navigation or manipulation. So what you need to do is something a bit more advanced, which is what we call learning as you go, or few shot learning, online learning, continual learning. And on that basis, what we have developed is neuromorphic computing, with, let's call it machine learning for the sake of simplifying things. And this basically does continual learning. So you don't need a huge data set as you usually do with deep learning and machine learning, but rather it takes a few shots from the environment and generates policy for the robotic arm to continue the navigation or the manipulation.
Okay, great. Thank you so much, Zied and Samaher. It was a really interesting talk, and I'm pretty sure a lot of people benefited, and they are maybe getting some ideas on how to implement AI in space, maybe solutions or healthcare. So maybe let's all thank the speaker, and I hope to see everyone next time. Thank you so much.
Yeah, thanks for having us. Have a lovely day. Bye-bye.
Bye. Bye-bye.